Hello everyone, today we're going to be working on the fundamental theorem of calculus. That comes in two parts, so let's dive right in. Before we begin, there's just a couple of terms that we need to know. The first one's going to be the antiderivative, which as the name would imply is the opposite of a derivative. So if you have f of x, that's an antiderivative of f prime of x being the derivative of f of x, and then if you go backwards, then f of x is the antiderivative. The next one is the definite integral, which is simply just the area under the curve of a function, which we'll have more about that in the next slide. Next, you have dx, which is an infinitely small amount of x. It is also referred to as the differential of x. And then there's just one property that we'll be using of integrals. Obviously, there's many more additive properties in this one, but it's if you go from a to b of the definite integral f of x dx, that is going to be the opposite of the integral from b to a. So here's a quick visual definition of integral for you. So obviously here's the a to b. This is the part of the integral we're talking about. So over here we have a and b. The blue line is the function, and then obviously x is x. And then dx, c, is going to be this infinitely small. I here drew it bigger so we can visualize it better, but it's the way that it works is from a to b, these two values down at the bottom, you multiply the height of the function, f of x, by this infinitely small width dx to make these sort of rectangles. And you'll notice that the one I drew in, there's this extra little area over here that's not being used. But when dx becomes infinitely small, as is the case with the integral, that area, or the extra area that isn't included in the rectangle, essentially stops existing. So each rectangle that you add up that's infinitely thin, added up between a and b, adds up to the area, the complete area under the curve. So anyway, the first part of the theorem states that the definite integral from a to b of some function equals that function's antiderivative at b minus the function's antiderivative at a. So here we have f prime of x and f of x, which is the derivative and the antiderivative. And we have a and b, which is not color-coded, apparently. So this is pretty simple. You'll also sometimes see this second part, the f of b minus f of a, written as f of x from a to b, but you would pronounce it as f of x evaluated from a to b. And that's just a shorthand for this other notation. The second part of this is you'll sometimes see, instead of f prime of x going to f of x, you'll see regular f of x going to a capital F. And it's mostly implied that when you have the capital F, also sometimes called big F, that it is the antiderivative of little f, but it is always good to state that explicitly. Anyway, let's move into this first example. So here we have the definite integral from 1 to 4 of x squared dx. So I'm not sure how much you've talked about antidifferentiation, which is just the process of going backwards, but the antiderivative of x squared is x cubed over 3. And you can tell because if you were to derive this, you would say 3 times x squared over 3 equals x squared. And that's just using the power rule. So then the next step is to expand this into the f of b minus f of a form. So we have 4 cubed over 3 minus 1 cubed over 3, which simplifies down nicely to 63 over 3, which is 21. And then you'll talk more about antidifferentiation later with other more complicated functions. That's neither here nor there. Anyway, for a more complicated example, here we have the definite integral again from 1 to 4, just to keep things simple, of x ln x dx. So I'm not going to go into super detailed why this is the antiderivative, but just take my word for it that it is x ln x minus x from 1 to 4. Then we expand this into the f of b minus f of a notation. So we have 4 ln 4 minus 4 minus, and then this all, you have to be careful about your parentheses in this one because this all is subtracted. So you subtract out the 1 ln 1, but then because you're subtracting out the 1 inside this function here, then you get, or then it adds back into the subtraction. So using some log properties, this coefficient up front of the 4 ln 4 is the same as ln of 4 to the 4th power, which is 256. Then it's minus 4, let's say it's the same. Ln of 1 is 0, and then because we're subtracting out the negative 1, we add it back in. So it ends up simplifying to ln of 256 minus 3. That's the final answer. Now let's move on to part 2. So this one, instead of being the integral of a derivative, this is the derivative of an integral. So this seems sort of complicated, and I'll go into more detail later. But if you have the derivative of the definite integral from a to some function of x, that's all this means, is that it's some function of x. It can be x, it can be x squared, it can be 2x, it doesn't matter, of f of t dt, that equals the function evaluated at the function of x times the derivative of the secondary function. You'll notice here that we use t and x, or we use t inside the integral instead of x. And that's because we're using x up here. It doesn't really matter what these two variables are, just so long as they are not the same, because if they were allowed to vary at the same time, then your variables are weird and it just doesn't work. So you have to use a dummy variable is what we call this. So the t is the dummy variable because we're using x over here, and then as long as this derivative is the same as this, then you're good. So let's go into an example. So here we have the derivative of the definite integral from 2 to x of t squared dt. So the first part is the x squared. So really what I should have done is, I can actually write it in. We have the t squared, the x gets plugged in to t, and it's squared, because this is the squared part. Then it's times the derivative of x, which is just 1. See, I wrote the derivative in pink. So the final answer is just x squared. If this is only x up here, you don't have to worry about chaining anything on using the chain rule, because that's essentially what's going on up here. And we'll go into more of a proof of this later, but essentially this is just the chain rule for this, and so you only need to worry about it if it's something other than x. So now for a more complicated example, let's do the natural log ln of t dt from -1 to x to 4x cubed, and the derivative of all that, ddx, definite integral 1 to -1 to 4x cubed, ln t dt. So the first step is to plug in this 4x cubed into x, or into t, excuse me. That is the f of x, the f of a of x part. Then you multiply by the derivative of the top function, and then that's it. Again, it is just as simple as you plug this top function into your the part you're integrating is the integrand. So the f of t dt is the integrand. You plug the a of x in for t, and then multiply with the derivative of a of x. The one thing you may see is if the function's on the bottom, and that just goes back to the other property that we talked about earlier. So you have this negative sign out front when you flip it over, and then it's just the same answer but negative. So now I'm going to go into a little bit of a proof. This is going to be the end of the example, so if you don't care too much about all of the why behind this, you can probably stop watching, but I think this is really interesting. So the first part about this is that the derivative of position is velocity, which I'm sure is a fact that you've covered before. In other words, v of t equals the derivative of h. It doesn't really matter how you define a position. It might be height, it might be distance, you might see s of t or h of t, but in essence, velocity, v of t, is the derivative h of t, h prime of t, which is the same as saying dh dt. These are just two different notations, whereas h prime is by Newton, dh dt is Leibniz. So, a similar, seemingly unrelated fact is that speed times time equals distance. If you're going 20 miles per hour for 1 hour, you've gone 20 miles. If you go 20 miles per hour, this is just a breakdown for 1 minute. 20 miles per hour is the same as 20 miles per 60 minutes. Times 1 minute is 1/3 of a mile. If you break down to a second, you go 1/180th of a mile. And you'll notice that as this time gets shorter, the distance you've traveled gets shorter. So in general, you can say that as your time tends to 0, the differential of t, the distance you traveled tends to 0, the differential of h. So you can, like I said earlier, the concept of an integral is adding up all these differentials. So in this case, the speed here is the v of t, the velocity, and then the time is just the time. So this dt and this v of t, or whatever we want to call the function, is this integral. So we have f of x, or v of t, times dt equals the integral of dh. And that's just the same thing as saying if you add up all of the differentials of the distance you've traveled, then that adds up to the total distance you've traveled, or in this case it would be displacement, because velocity takes distance or direction into account. So this sort of wordy definition basically just says that if you add up at each instant how far you've traveled in that instant, or for each dt, the dh, if you add up all of the dh's, positive or negative, you get how far you've traveled. But since we already know that displacement is your position at the end minus your position in the first place, which is just the definition of displacement, you can then prove, therefore, that this integral over here is the same as this quantity h of b minus h of a. So that's the proof for the first part. The second part follows pretty closely behind. This is just a reminder of what the second part says. The derivative of the integral from a to a of x of f of t dt is f of a of x times a prime of x. So, if we start here, this is the first part. This is using exactly only what's in the first part of the fundamental theorem of calculus. So here's essentially f of b, which is, instead of b, we're using a of x, so that's this, minus f of a, which is the first part in its entirety. And then we are noting that big F prime of t is f of t. And I use t as a dummy variable because we don't really want to focus on this a of x in the chain rule, because if we were to focus on f prime of a of x, you'd get chain rule, and we don't care about that right now. Big F is an antiderivative of little f. From here we can derive, so this derivation of this right side, which is this, is the same as this derivation of the left side, because this is an equality that we've already established. From here, we can show that this is just a distribution. This is a sum property of derivatives. So the derivative of f of a of x minus the derivative of f of a, and because f of a is a constant, this is going to derive to 0, and this is just going to apply the chain rule. So the derivative of a compound function is the derivative of the outside function of the inside function, so f prime of a of x times the derivative of the inside function times a prime of x minus 0, because this is a constant. And then because we noted earlier that this relationship of derivatives exists, we can sub f prime of n for f. And then this is the original thing that we started with, QED.